Hello, everyone, and welcome to the Environmental Science and Engineering Podcast channel. We're going to be diving deep into some really cool stuff today. So if you're into this kind of thing, go ahead and hit that subscribe button. All right, so today we're tackling a fascinating area in environmental engineering. You guessed it, membrane bioreactors, MBR for short. I've been looking over the material you sent over, and wow, there's a lot to unpack here. Our mission today is to break it all down, understand why it matters, and really highlight what makes this technology so intriguing. We're going to cover its history, how it's being used globally, its technical advantages, and of course, some of the challenges engineers are working to overcome. We'll keep it conversational, a nice question and answer flow, but still technical, of course. Don't forget to subscribe to the channel and leave a comment below when we're done. Now, to kick things off, what sparked the interest in MBR technology in the first place?
Well, the earliest work on MBR technology actually goes back to 1969 with Dore Oliver Inc. They had some pretty impressive results even back then in terms of water quality, but there were a couple of major obstacles that prevented widespread adoption.
I see. What were those?
High energy consumption and, you guessed it, membrane fouling.
Fouling.
Yeah.
It always seems to come up. So what was the breakthrough that really propelled MBR into the mainstream?
The major turning point was in 1989 when Yamamoto and his team introduced the submerged membrane configuration. Putting the membrane directly into the bioreactor, submerged in that mix of water and microorganisms, really changed the game. It simplified the process, made it much more practical. That innovation was a catalyst for the widespread use of MBR we see today.
Makes sense. So from those early efforts to the submerged design, when did MBR transition from emerging technology to something engineers would actually rely on?
It was really after the year 2000 that MBR earned its stripes as a mature technology. It became well established for both industrial and municipal wastewater treatment. All that research and development in the preceding decades paid off.
All right. That gives us a good historical perspective. Now, let's zoom out a bit. How big is MBR on a global scale today?
It's pretty significant. We're looking at a global market of about 3.35 billion US dollars and growing at a solid 7% annually.
7% growth. That's impressive for a mature technology. So where is MBR most prevalent geographically?
Globally, there are over 5,000 MBR plants in operation. And currently, China has the largest number of installations. They've really invested heavily in upgrading their wastewater treatment infrastructure.
Over 5,000 plants. That's a lot. Are we talking about mostly huge centralized systems?
While large-scale applications are a big part of it, there are also many smaller systems. We have 63 large-scale MBR plants globally, each treating over 100,000 cubic meters of wastewater per day. They are mainly in China, the US, and Europe.
Okay, so big projects are definitely happening, but given MBR's compact nature, what about smaller scale needs?
You're right. MBR is incredibly valuable in smaller, decentralized applications. Think individual buildings, industrial sites, airports, even offices. Because MBR requires less space than traditional wastewater treatment, it's perfect where land is limited, like in urban areas.
Makes sense, especially in crowded cities. So beyond just treating wastewater, are there other benefits in these smaller setups?
Absolutely. Water recovery and reuse are common. Because MBRs are so efficient, the treated water can be used for things like irrigation, toilet flushing, even cooling systems. It helps reduce water consumption and costs, especially relevant as water scarcity becomes a bigger issue.
That's huge, especially with water becoming such a precious resource. Now let's dig into the engineering side a bit. Why would an engineer opt for MBR over traditional wastewater treatment?
There are several reasons. We've already talked about the compact design, which is a huge advantage. It's just more practical in many situations. Imagine trying to fit a conventional treatment plant inside a building. That's where MBR shines.
So space efficiency is a major plus. Can you walk us through how MBR separates clean water from the sludge?
Sure, traditional wastewater treatment relies on a secondary settling tank. Wastewater flows into a big tank, the heavier sludge settles to the bottom by gravity, and the clearer water is collected from the top. MBR eliminates this secondary settling step altogether. The membrane itself acts as a physical barrier, filtering out the biomass and leaving you with clean water.
Interesting. So direct filtration instead of gravity separation. You mentioned MBR can handle higher concentrations of biomass, specifically the term MLSS. Can you explain what that is and why it's beneficial?
MLSS stands for Mixed Liquor Suspended Solids. It basically refers to the density of microorganisms in the bioreactor. MBR systems can maintain much higher MLSS levels in the range of 8,000 to 12,000 milligrams per liter, significantly higher than conventional systems. This means more microorganisms are working to break down pollutants, making the process much more efficient.
Got it. So it's like having a superpowered cleaning crew. Can engineers fine-tune the treatment process more precisely with MBR compared to traditional methods?
Definitely. MBR allows independent control of SRT, sludge retention time, and HRT, hydraulic retention time. SRT determines how long the microorganisms stay in the system to do their job, and HRT is how long the wastewater itself is treated. MBR gives you flexibility to adjust these independently, optimizing the process for specific types of wastewater and effluent quality targets.
That level of control seems really valuable. What about the quality of the treated water? How does it stack up?
The water quality from MBR is generally excellent. In fact, it often surpasses conventional secondary treatment, often eliminating the need for additional tertiary treatment steps, which would normally be needed for water reuse. And because the membrane acts as a physical barrier, it removes virtually all pathogenic bacteria, making the water much safer for reuse.
It sounds almost too good to be true. But I know there must be some challenges. What's the main operational headache with MBR?
The biggest challenge is, as we mentioned earlier, membrane fouling. Substances in the wastewater build up on the membrane surface or in the pores, making it harder for water to pass through. This causes a decrease in flux, which is the flow rate of clean water, and an increase in transmembrane pressure, which is the pressure needed to push water through the membrane. Ultimately, it leads to more frequent cleaning or even membrane replacement.
Right, fouling. So how does that impact the day-to-day operation of an MBR plant?
Well, fouling means you need more energy to pump the water through the membrane, so higher electricity costs. It also reduces the lifespan of the membrane, meaning more frequent cleanings and replacements, which adds to the operational costs and complexity.
So fouling really hits you in the wallet.
Ugh.
Are the upfront costs of an MBR system also higher compared to conventional treatment?
Yes, generally the initial investment for an MBR system is higher than for a conventional plant with similar capacity. And as we discussed, the operating expenses, especially for energy and membrane maintenance, also tend to be higher. It's a trade-off between the benefits of MBR and those cost factors.
Okay, so understanding those costs is crucial. Let's talk about the membranes themselves. What materials are commonly used to make them?
The most common materials are synthetic polymers, things like PVDF, polyvinyl fluoride, PES, polyether sulfone, PSF, polysulfone, and CA, cellulose acetate.
And are all these materials equally preferred, or is there a front runner?
PVDF is generally preferred because it's very durable and resistant to chemicals. It can handle the tough conditions of wastewater treatment and the chemicals used for cleaning.
Makes sense. And what about ceramic membranes? Are those used in MBR?
Ceramic membranes are an option, and they are even more durable than polymers. But they are also more expensive to produce because they require high-temperature manufacturing. So for now, polymer membranes are more common due to their balance of performance and cost.
Practicality wins again. So how are these membranes physically configured within an MBR system? What are the common forms?
There are four main configurations. You have flat sheet membranes, which are basically flat sheets, often used in smaller pilot systems. Then there are spiral wound modules, which pack a lot of membrane area into a compact cylindrical shape. Hollow fiber membranes are very efficient in terms of space. They're like bundles of thin tubes. Finally, tubular membranes have larger channels and are used when the wastewater has a lot of solids.
So different designs for different needs. And what size particles can these membranes typically filter out?
MBR membranes usually fall in the microfiltration, MS, and ultrafiltration, UF range. This means they can remove suspended solids, bacteria, and even some viruses, ensuring high water quality.
Let's go back to the elephant in the room, membrane fouling. Can you explain exactly how it happens?
Sure, there are two main processes. First, you have the physical clogging of the membrane, pores by particles and dissolved substances. Second, a biofilm or cake layer forms on the membrane surface. This layer is a mix of microorganisms, organic matter, and particles that stick to the membrane, creating a barrier to water flow.
Okay, so there's a double whammy. And what are the main culprits causing this fouling?
Mostly organic substances, which are categorized into EPS, SMP, and DOM. EPS, extracellular polymeric substances, are sticky substances produced by microorganisms. They contribute to biofilm formation. Then you have SMP, soluble microbial products, which are organic compounds released by microorganisms. These can clog the membrane pores. And finally, DOM, dissolved organic matter, is a broad category that includes all dissolved organic compounds in the wastewater. Different types of DOM can contribute to both surface and pore fouling.
So a real mix of organic troublemakers. How do you know when a membrane is starting to foul?
The main indicators are an increase in transmembrane pressure and a decrease in flux. As fouling increases, you need more pressure to maintain the same flow rate, or the flow rate decreases if the pressure is kept constant.
It sounds like a constant monitoring game. And is all fouling the same, or are there different types?
There are three main types of fouling. Reversible fouling is the easiest to deal with. You can remove it with physical cleaning methods. Irreversible fouling requires chemical cleaning. Then you have permanent fouling, which is basically irreversible damage. Knowing which type you're dealing with is crucial for deciding how to clean the membrane and managing the costs.
Okay, so fouling is not a one-size-fits-all problem.
Yeah.
Now, let's talk about the microbial community in an MBR. What kind of microorganisms live in there?
One cool thing about MBRs is they can support slow-growing bacteria, which are often better at breaking down tough organic pollutants.
But don't those same microorganisms contribute to fouling? It seems a bit ironic.
Yeah, it's a bit of a catch-22. These microorganisms produce the EPS and SMP that cause fouling, but they are also the ones cleaning the water.
Necessary evil, I guess. So what are some of the key players in this microbial community?
It's a pretty diverse bunch. Bacteria are the main actors, especially groups like proteobacteria. You also have protozoa and metazoa, which are larger microorganisms that help keep things clean. Filamentous bacteria, algae, and fungi can also be present. The exact composition depends on the wastewater and the operating conditions.
And what is the specific role of bacteria in all of this?
Bacteria are the real workhorses when it comes to removing pollutants. They break down most of the organic matter in the wastewater. Their efficiency depends on their growth rate, how well they can utilize the available food sources, and their kinetic coefficients, which determine how fast they can perform their biochemical reactions.
Right, the bacteria are the heavy lifters. Now back to the engineering side. What are the main ways to configure an MBR system?
The two most common configurations are submerged and external.
Can you briefly explain each of those?
In a submerged MBR, the membranes are directly placed inside the bioreactor, surrounded by the microorganisms in wastewater. In an external MBR, the membranes are in a separate unit outside the bioreactor. The wastewater is pumped through the external membrane unit for filtration and then returned to the bioreactor.
Two different approaches to the same goal. Are there any other types of MBR systems out there?
Yes, there are some more specialized MBR configurations being developed. We have NMBRs, or anaerobic MBRs, which are great for treating high-strength wastewater and producing biogas. Then there are hybrid systems like AFMBRs, MPBRs, and MFC MBRs, which combine MBR with other technologies to enhance treatment or generate energy. These specialized systems could be a topic for another deep dive sometime.
They certainly sound interesting. Looking ahead, what are the main goals driving future developments in MBR technology?
The main focus is on reducing energy consumption, extending membrane lifespan, and making the membranes more affordable.
Makes sense. And how are researchers trying to achieve these goals?
A lot of research is going into creating better membranes that are more resistant to fouling. They are experimenting with different surface modifications, like making the membrane less hydrophobic, changing its surface charge, and creating smoother surfaces to prevent things from sticking.
It sounds like they're really getting down to the nitty-gritty. Are there any other areas for improvement?
Yes, making MBR systems more durable and less susceptible to seasonal changes in wastewater is important. They're also trying to optimize plant design and operation to save energy, for example, by improving aeration and control systems.
And what about new materials? Anything exciting on the horizon?
Absolutely. Researchers are exploring new materials like nanocomposites and incorporating additives like Ag3PO4G, C3N4, and lignin to improve membrane performance and durability.
Well, that was quite a journey through the world of MBR technology. We covered a lot of ground, from its history and global use to its technical advantages and challenges. What I find really compelling is how MBR balances compact design with high-quality treatment, opening up possibilities for both large and small-scale applications.
And that brings us to an important question for you, our listeners. Given the potential of MBR for water recovery and reuse, where do you see the biggest opportunities for this technology in the future? How can it contribute to solving water scarcity and promoting sustainability?
It's a great question to ponder. As cities grow and water resources become more strained, MBR could play a crucial role, particularly in water-stressed regions and industries with high water demands.
We hope you enjoyed this deep dive into MBR technology. It's a field that's constantly evolving, and we're excited to see what the future holds. Don't forget to subscribe to our channel for more insightful discussions on environmental science and engineering. And please leave a comment below with your thoughts and questions. We always love hearing from you.
Thank you for joining us today. We hope you found this deep dive informative and engaging. Until next time, keep exploring the amazing world of environmental science and engineering. And remember to subscribe and leave a comment below.